In this session, we will deal with the topic bevel gear. First, let us have some facts regarding the bevel gear and we will forward with the design procedure. Bevel gears are basically cut on two conical blanks, and it is mainly used to transmit the rotation or the power between intersecting as well as non-intersecting shaft. So, when compared with the spur gear and helical gear, if we want to transmit the power between two shafts which are not parallel, then we have to go for the bevel gear. And when we look into the features of the teeth and the geometry of the bevel gear, it can be noted that the tooth shape for the bevel gear is determined by scaling spur gear tooth shapes along the face width. That means, if we look at this bevel gear teeth, you can see that it is somewhat very much similar to that of a spur gear, but it is scaled. The teeth of a spur gear is scaled to some extent to obtain the teeth of a bevel gear. We will discuss the different types of bevel gears in the coming slides. Anyway, now let us focus on the topic that we discuss here. And the tooth cross section at the largest part of the tooth is identical to the tooth cross section of a spur gear with pitch diameter 2 RB. RB is the length from the axis to the face, that I will explain right after this. Anyway, if you cross check it over here, we can see that the shape of this teeth is same as that of the shape of a spur gear, and we are talking about this particular plane and with imaginary number of teeth. That means, if we consider the tooth of a bevel gear, it is very much resembled to the spur gear at the pitch diameter of 2 RB and with an imaginary number of teeth. That means, here also we have to consider an equivalent spur gear with imaginary number of teeth. And one most important factor of this bevel gear is that one wheel of a bevel gear is designed to work with its complementary wheel and not others. That means, the interchangeability is an issue. So, it is specifically designed for one particular set. So, we cannot change that one. If you want to change, you have to change the entire set. That is what is the meaning. That means, it has to be precisely mounted, and the shaft, the supporting shaft should also be able to support significant forces, because here also the plane of force is something different. You have to consider the force system in space, like we have discussed for the helical gears. So, these are some of the basic facts of the bevel gear, and we have to discuss the different types of bevel gear. See, bevel gear are mainly classified, it has got different classification. Among that, we will discuss a few. One is that a straight bevel gear. As the name indicates, we can see the teeth are straight on the circumference, on the surface of the cone. In the previous slide, we have discussed about the conical blanks. So, if we consider these spur gear and if we extend this tooth, these two form two cones which are touching each other on the surface, and part of the cone is being cut away, and finally we obtain this shape. And this is the fundamental concept of the bevel gear, and you can see that the teeth are straight. That is called as the right circular cone. That means, these teeth are on the right circular surface of the right circular cone. Its tip is cut off, and the fact is that their axis also intersect at this point, forming an arbitrary non-straight angle between the shaft. Please do not get confused. Here it is 90 degree, yes, that is right, but it is stated that non-straight angle between the shaft. That means, you can have a straight bevel gear which transmits power between shaft from an angle, or which are located at an angle ranging from 0 to 180 degree, not just 90 degree. You can have a bevel gear that transmit power between shaft which are aligned at some angle between 0 to 180. That is what the meaning of a straight bevel gear. Anyway, we will discuss the various classification under the straight bevel gear in the coming slides. And the second one is the spiral bevel gear. The spiral bevel gear, when you compare with the straight bevel gear, it is one of the same, but the teeth are in a spiral form, something like we have discussed in the helical gear. There also you had the we discussed about the spherical type of bevel gear, and the features of this teeth are same when we compare with the bevel gear, because this help the smooth engagement of the teeth, and at least two teeth will be in contact at a time, and this reduces the load on the single teeth. If you consider here a single teeth may be in contact, but here definitely two will be in contact. So, the load will be shared between two teeth, and because of that it is smooth and it can run 8 times faster, and all these are the interesting facts of this spiral type of bevel gear. So, usually when it comes to the higher loading application or even higher speed application, we will prefer the spiral bevel gear than the straight bevel gear. These are some of the facts. Now comes the meter gear. The name is completely different. Meter gear looks very much similar to that of a straight bevel gear, but what is the difference? The main difference is that in a meter gear, the number of teeth on both the wheels, both the gears are one of the same, and they are 90° apart. These are called as meter gear. So, without stating the angle between the axes, they can simply state that meter gear. If it is stated like meter gear, definitely you have to choose same number of teeth for the pinion and the gear. And finally, we have the hypoid gears. You may be wondering what is the difference between this hypoid gear and a spiral bevel gear, because we have got a spiral type of teeth here, a spiral type of teeth here on the pinion and the gear, but it is being stated as hypoid gears. The fact is that if you check the line of the shaft, and this is the center of the gear, look here, these are not intersecting. That is the reason why I have discussed about in the first slide about the intersecting as well as non-intersecting shaft. Okay, the figure which is given here, this is a hypoid gear, because the axis of the shaft, both the shafts are not intersecting, but that is not the case here. If you take the axis here, it will intersect at a particular point, forming a right circular cone. So, when it comes to the case of a hypoid gears, so the axis of the shaft are not intersecting, and this is mainly used to connect the drive shaft to the rear axle of the automobile. Does not mean that always the shaft of the the shaft or the driving shaft that is coming from the gearbox we should be in line with the differential. No, it can, but we cannot always ensure that it will be in line. So, if that is the case, hypoid gears are the best option, because it provides the feasibility of transmitting power between shaft which are not intersecting. And moving forward, this is the basic nomenclatures and the variables that we use in the bevel gears. So, this is called as the Corne distance. If you consider this, right now we have discussed about a right circular cone. If you look here, it is easy for you to understand. If you look here, you can see this particular cone. This is one circular cone, right circular cone, and this one is the another circular cone, something like this. So, this is definitely a right angle bevel gear. The axis is perpendicular to each other and intersecting at a particular point. Now, we have to discuss about the corne distance. Corne distance means the distance from this particular point, tip of the corne to the edge of the farther edge of the teeth, that is called as the corne distance. And we have got pitch apex to back length, pitch apex to the crown. This portion is called as crown. And another important, this distance is called as the back corne distance. Okay, this distance RB is called as the back corne distance, and this back Corne distance is specified here in the slide. This 2 RB, RB is nothing but the back Corne distance, and this RB, and at this point RB we are defining an equivalence per gear. That is one of the most important point that you have to keep in your mind, that we are considering an equivalence per gear for the design of this bevel gear, and that equivalence per gear is considered a distance RB from the point B, and this is called as the pitch diameter, and all these points are very much similar. You can easily understand the nomenclatures for the bevel gear, and the angle that we have to discuss here is the pitch angle, or otherwise it is called as the semi-cone angle. Semi-cone angle is the angle between the axis of the shaft to this, or it is stated as pitch angle, or otherwise it can also be called as semi-cone angle. Cone angle, suppose if they give the cone angle, you have to take half the value of that to get the semi-cone angle, and we will be using the semi-cone angle for the design of the bevel gear, that you have to keep in your mind. And like we discussed about in the spur gear, we have got addendum, dedendum, the depth, the width, all those things are very much similar. This is called as the face, this length is called as the face. If you take a spur gear, this is called as the face, okay. And the geometry or the profile that we use is same as that of this spur gear, 14.5 degree in value, 20 degree, like that the profiles are one and the same. Now we have to define an equivalent spur gear for the design, and that equivalent spur gear will be having a number of teeth, formative number of teeth equal to ZB, and the equation that we will be using is Z by cos delta. This is the basic equation that we are going to deal with, and obviously the gear ratio that does not change for any gear, even if you consider the spur gear or even if you consider the helical gear, bevel gear, everything, the gear ratio remains the same, d2 by d1, z2 by z1, n1 by n2, everything. Okay. Now moving forward, in the design we will be mainly focusing on the straight bevel gears. We are not designing the spiral type bevel gears, we will be designing the straight bevel gears. The straight bevel gears are mainly of 3 types. One is the obtuse angle bevel gear, second one is the acute angle bevel gear, and the third one is the right angle bevel gear. I think the name is self-explanatory. If you look at the axis between the shaft, look here, this is the axis between the angle between the axis of the shaft. This is greater than 90 degree, so it is called as an obtuse angle bevel gear. And if the axis between the shaft, transmitting shaft, is less than 90, that is called as acute angle bevel gear. And finally, if it is 90 degree, it is called as the right angle bevel gear. So the data book will be in the data book, the design is focused on mainly these 3 categories. Okay, we are not going to discuss about the spiral type or the any other type. Meter gear definitely we will be discussing, but spiral bevel gear we are not focusing. Straight bevel gears with the angle less than 90, equal to 90 and greater than 90. These 3 are the focus of the discussion for the further section. Now let us discuss about the design procedure, how we have to design it. So initially, all the initial steps remains the same, because you have to write down the allowable stress for the pinion and gear. You have to calculate the Z1 and Z2 for the type 1 problem, and also you have to calculate the formative number of teeth Z1B and Z2B using the equation 12.35D, and also you should have the N1 and N2. All these data should be readily available with you for the design. Now let us move to the data book. We will discuss a few points in the data handbook, then we will come back here and we will discuss the design procedure. So if you go to the data handbook, see from here you can see this is the helical gear, and moving forward we can see the details of the bevel gear. See the image is right over here, the pitch, cone, length, L, B, all these things are very familiar to you. So the figures are readily available there in your data handbook, and the different types of bevel gear, special type, typical type, meter gear, all those things are given here, the nomenclatures, everything. And if you look at the design of the bevel gear, we can see that 3 sessions. One is for the acute angle bevel gear, other one is the obtuse angle bevel gear, and the third one is the right angle bevel gear. You have got separate set of equations for the bevel gear. Okay. Now, if you look here, you can see the equations for the equivalent number of teeth, Z divided by cos delta. So, delta is nothing but the pitch cone angle that we have already discussed, half pitch cone angle or half cone angle, semi cone angle, like that. So, we have to calculate the delta 1 and delta 2. Delta 1 indicates the semi cone angle for the pinion, and delta 2 indicates semi cone angle for the gear. And all the datas, what is phase angle, all those things are given here. Now, let us move to the discussion on the design. Now, so the design procedure remains one of the same. We have to use the formative number of teeth ZV1 and ZV2 or Z2V for the calculation of Y1 and Y2. Y1 and Y2 is nothing but the formative number of, Lewis form factor. So, this Lewis form factor is used along with the stress value to get the value of sigma y, and among these two the weaker one will be the smaller one, or the smallest value among these two will be called as is the weaker one, and we have to design for the weaker member. The small value among the sigma 1 y1 and sigma 2 y2 is the weaker one, and this procedure remains the same. And finally, if you move forward, the equation for the tangential tooth plot remains the same, 1000 p CS by V. CS is service factor, same as that of the spur gear. Velocity we have to substitute in terms of module. Here we have only one module M, not like helical gear. We have got only one module M. There is no Mn or Mt. It is only one module M. So, substitute the velocity in terms of module and obtain the Ft value in terms of module. And moving forward, we will calculate the tangential load using the Lewis equation. So, Lewis equation, all the terms are very much familiar to you. Sigma is the static stress of the weaker member, B is the phase width. We will be using the equation 12.368. We will go to the data handbook and we will look into the equation, or we will be using the 10m. This is same for all the gear that we use. And Y is the same Lewis form factor, which is nothing but pi into Y. And L is the cone length that we have already discussed in the data handbook. B is, and here the most important thing is that this L has to be substituted in terms of B. Substitute the value of L in terms of B. That is the important thing that we will go to the data handbook and we will look into that and we will see. And after this step, we are going to get an M cube CV equation, and we have to solve by using the trial and error method to get the value of module. And after getting the module, we have to standardize the module. Now, let us go to the data handbook and see what all are the equations given corresponding for that. And see, this procedure remains the same, but some calculation are in excess. Okay, so let us discuss what are the changes that you have to carry, what are the changes in the design procedure, or what are the additional calculation that you have to make. First of all, the formative number of teeth. Let us discuss from here. Formative number of teeth. If you look here, you can see that the formative number of teeth consists of ZE equal to Z divided by cos delta. Now, the question is, what is delta? Delta is the semi-cone angle. So, this delta has to be calculated. So, how we can calculate the value of delta? Delta is calculated based upon the angle of the shaft. If it is an acute angle bevel gear, delta and delta 1 and delta 2 can be calculated using the equation 12.29a and 12.29b. And you have a theta mentioned over here. What is this theta? Theta is nothing but the angle between the shaft. Suppose if you have an acute angle bevel gear and the angle between the shaft is some 60 degrees, and the value of theta has to be substituted as 60 degree. And Z1 and Z2 are the actual number of teeth on the pinion and gear. It is not the formative number of teeth. It has to be the actual number of teeth. Suppose if the angle between the shaft is an obtuse greater than 90 degree, you will be using the equation 12.31a, 12.31b. You will calculate the value of delta 1 and delta 2. And if it is 90 degree, we will be using this equation 12.32a and 12.32b. And the L also can be calculated using this equation, but if diameters are unknown, you cannot calculate the value of L. Anyway, by using these set of equations, you have to calculate the value of delta 1, delta 2, and use that delta 1 here, delta 2 here to get the value of the formative number of teeth. This is an additional calculation you have to carry out before you find the number of teeth on the equivalent spur gear. And further we will be using the equation 12.37. Here you can see the equation sigma d Cv b by m L minus b by L. Here you have to substitute the L in terms of b. For that, if you look here, you can see that is not okay. This L has to be substituted like this. It should be b should be less than or equal to L by 3. So if you consider b is equal to L by 3, then L will be equal to 3b. Like that, you have to substitute here. So ultimately the b will get cancelled, or the other way, if you substitute in terms of b in terms of L also, no issue, b equal to L by 3, then also L will get cancelled out. Anyway, this equation 12.36b has to be used for the substitution of L or b, and b will be substituted as 10m. So please, it will be better if you go with the substitution L equal to 3b, that is sufficient. Okay. And here another option is there, b is varying from 6m to 7m or from 7m to 10m if L is greater than 30m or the L is less than 30. So basically, since we are going to find out the module, we don't have the we cannot conclude this. So because of that, we are going to substitute the value of b as 10m itself. Okay. And if you have the module initially, based upon the module and based upon the values of L, you can select the width of face width. That is another criteria for the design. Anyway, for the time being, ft has to be substituted in terms of module, b will be 10m and another m is here. So altogether we are going to get m cube Cv. Okay. And the equations for the Cv is 12.38a and 12.38b. So use these two equations to find the value of, we will assume the module, we will calculate the velocity, followed by the calculation of Cv, and then finally m cube Cv. And I think that procedure is very much clear to you right now. You simply follow that procedure. Only thing is the changes in the equation. You have to note down the changes in the equation. And in the next step, you have to calculate all the physical dimensions. The physical dimensions can be calculated using the equations given under corresponding bevel gears. The outer diameter, the inner diameter, d1, d2, all those things can easily be calculated, and followed by the calculation of dynamic load. Dynamic load can be calculated using the equation 12.40. All the equation is very much similar, same as that of the spur gear. So I think there is no need to explain this equation once again. If you have got any kind of confusion in calculating the dynamic load, kindly refer the video of spur gear, design of spur gear, and there I have explained clearly how the details about the calculation of ft, and followed by the wear load. So wear load Fw is obtained from the equation 12.41. So here you have to use delta 1 and d1 obviously for the pinion. And also one of the important thing you have to note down here is for the calculation of Q, you will be using the formative number of teeth, and that is not the case for helical gear. There we use the actual number of teeth, but for the case of bevel gear, you have to use the formative number of teeth for the calculation of Q. This much is the points that you have to keep in your mind when you discuss the design of the bevel gear. Everything is given here, and finally you know how to conclude the design by equating Fw with Fd and getting the value of K and solving for K. So you get the value of K, and from the table you can select the suitable hardness. Now let us go to the tables corresponding to the bevel gear and see what are the features, additional informations given in the tables for the bevel gear. So if you consider the bevel gear, you can see here bevel teeth. See after the table 12.22, from 12.23a onwards you have the proportion for the bevel gear. So to find out the dimensions and the step number 4, you can use the table 12.23a. The addendum, dedendum, all these values are can be obtained using the module. Okay, using the module. Look here, these are the area where the dimensions can be obtained. And finally, if you move forward, you can see the standard modules. So, after the step number 3, you have to use the table 12.24 for the standardization of the module. Then this is for the worm. So, only a very few sets of tables are given for the bevel gear. So, whatever data are sufficient required for the design has to be obtained from the data of the spar gear. So, only 3 or 4 tables are given for the bevel gear, because the reason is that the design is very much similar to that of the spar gear. So, for the static stress, for the CV calculation, for the Y calculation, all those things you can refer back to the spar gear equations and use this set of tables for the calculation of the proportions of the bevel gear and for standardizing the module. So, these are the factors. So, when compared with the helical gear, bevel gears are very much simple in design, even though it has got compared to the design procedure of a helical gear, the bevel gear are very much similar to that of the spar gear and it is very simple. So, kindly cross check the designs of spar gear, helical gear and bevel gear. You can understand that the pattern of the design is very much similar, the equation is also very much similar. Definitely there is changes, you can see similar equations. So, kindly note down what are the changes, what are the specialities of the design. So, what are the changes when we design a helical gear when compared with the spar gear. So, what are the changes in the design of a bevel gear when we compare it with the spar gear and helical gear. Like that, you have to understand the design procedure. So, please do not blindly by heart the design procedure. No, understand each step, how the substitution is being carried out. All those things has to be kept in your mind before you proceed with the design. Definitely, here also we have got 2 sets of problem. First is a type 1 mod, type 2. Type 1 will deal with the number of teeth given, and at the type 2, the diameters or the velocity or the center distance will be given. So, you have to understand the question very clearly before stepping into the design procedure, and after obtaining all these data, kindly solve the bevel gear and design the bevel gear. And that's all for now. We will meet again with the design problem of a bevel gear. Thank you.